Part 2 of Chapter 18. Here we're looking at the endocrine pancreas. And the pancreas is both an endocrine and an exocrine gland. By referring to it as an endocrine gland, it indicates that it is going to secrete a hormone of some sort. The exocrine component is that it secretes a digestive enzyme. This gland sits behind the stomach, so it allows for the exocrine component to be in very close proximity to the intestine, where it can dump, so to speak, the digestive enzymes that are produced and move directly into the intestinal tract. So within the endocrine pancreas, there are 4 major types of cells. You have the alpha cells, which secrete glucagon, the beta cells that secrete insulin and amylin, the delta cells that secrete gastrin and somatostatin, which we will not get into, and the F cells that secrete pancreatic polypeptide, which we also will not go into. But rather, we're going to focus mainly on insulin and glucagon. Insulin, as stated on the previous slide, is secreted from beta cells. Insulin functions mainly in the liver, the muscles, and then fat cells. The secretion of insulin is promoted by increased blood glucose levels, generally after you eat. And what insulin does is simply facilitates or stimulates the rate of glucose uptake into the cells of the body. It's also interesting to note that it's synthesized from proinsulin, which means that insulin is in an unusable form as proinsulin. And so then it has to have an enzyme that comes in and digests that proinsulin protein to actually allow it to be functional. Right, it's also classified as an anabolic hormone, meaning it's going to play a role in the synthesis of proteins, lipids, and nucleic acids. Now, glucagon is secreted by alpha cells. Secretion of glucagon is promoted by decreased blood glucose levels, and glucagon functions mainly in the liver, and its function is to increase blood glucose levels. It stimulates glycogenolysis, gluconeogenesis, and lipolysis. Glyconeolysis is the formation of glucose from non-carbohydrate molecules, such as lactate, pyruvate, amino acids, and glycerol. So if you can imagine, if you are not pulling in the proper amount of glucose, your body can then start utilizing other materials. The adrenal cortex. This is a pyramid-shaped organ above the kidneys, so that means there's 2 of them. It has a capsule, the outer cortex, and then the inner medulla. The adrenal cortex is going to be stimulated by the excretion of adrenocorticotropic hormone, or ACTH. This comes from the pituitary. What this hormone allows is the utilization of cholesterol, and the gland will use cholesterol to synthesize hormones. So, a small amount of cholesterol is necessary for life. It acts to secrete, the adrenal cortex, acts to secrete glucocorticoid hormones. These are going to have direct effects on carbohydrate metabolism. They can be anti-inflammatory and growth suppressing. They influence awareness and sleep habits, and they are actually the most naturally occurring glucocorticoid is cortisol. Cortisol is a primarily secreted hormone. It's regulated by the hypothalamus and the pituitary, and it is absolutely necessary for the stress response. All right, in addition, You have the mineralocorticoid hormones. These affect ion transport of epithelial cells, so increasing the activity of the sodium pump. The mineralocorticoid hormones cause sodium retention, potassium and hydrogen loss. And the most potent, naturally occurring one is aldosterone. And this is going to be regulated by the renin-angiotensin system. So you may actually want to go back and refer to chapter, let's go with chapter 5 material. I think that's what it is for the 6th edition. And here is aldosterone regulation. Figure 1817. Again, this should be quite familiar to you. You have increased aldosterone levels. Aldosterone is going to act to increase sodium and water reabsorption from the kidney, to have increased effective blood volume to correct the initial stimulus to the system, whatever that was, decreased renal blood flow, hypovolemia, hypotension up here, sympathetic input. This is the nervous system activity that is then going to have a direct effect on the endocrine system. All right, endocrine in terms of all of these 3 different things, these stimulating variables: decreased renal blood flow, sympathetic input, act on the kidney, all right, to release renin. Renin acts on angiotensinogen to create angiotensin 1. Angiotensin 1 converting enzyme, or ACE, is found in the lungs that breaks down angiotensin 1 to angiotensin 2. That causes increased secretion of aldosterone. This can also, increased aldosterone levels can be activated by hyponatremia, hyperkalemia, too much phosphate, or maybe that's potassium, I'll have to check, or ACTH levels. So, real fast, if I were in class, I'd be asking one of you to correct me, and it is chapter 5. And it's potassium, all right? Too much potassium will cause an increase in aldosterone levels. Too little sodium, increased aldosterone levels to cause the kidneys to hold on to sodium and water. Again, overall effect of aldosterone, increase effective blood volume. That will then really affect or increase blood pressure. All right, and the last slide for chapter 18 is just looking at the adrenal medulla. Here are found chromaffin cells, and the chromaffin cells secrete the catecholamines. Epinephrine is the main one, but it can also secrete norepinephrine. And these hormones are going to be involved in the fight or flight response. And sometimes today, if you are in a particular profession, whether it's the counseling area or whatnot, there's another F that can be combined with that: fight, flight, or freeze response, all dictated by epinephrine, adrenaline, those type of hormones. And the catecholamines also promote hyperglycemia. So that is going to be the end of chapter 18 material. Really just somewhat of a review, possibly, of the different glands within the endocrine system. Chapter 19 is where we will start talking about all the different diseases and eruptions to proper function of the endocrine system.